We have seen many gigapixel-sized images and viewers that allow interaction to pan and zoom to explore the great detail they contain. This provides a sense of immersion and exploration, but the imagery itself is static. The gigapixel images are created by stitching multiple images captured over a span of minutes. To date, it is impossible to capture frame rate video at such a large scale. However, it is possible to capture full-speed video of small regions of the overall gigapixel image to add dynamic elements to the panorama. This trade-off between space and time presents challenges for creating a seamless viewing experience. Artifacts occur if a video starts or stops playing when in view. Other artifacts occur if the current view window overlaps the edge of the video. Carefully controlling the pan and zoom as well as timing the start and stop of the videos can hide most of these artifacts from the viewer. Both the dynamic view and timing of the video playback are jointly optimized. We capture the gigapixel panorama using an SLR with a long lens mounted to a gigapan to scan the scene. The individual shots are stitched using the Microsoft Image Composite Editor. The same camera and lens is then used to record video clips manually aimed to capture items of interest. The first task is to align the video within the stitched gigapixel panorama. We do this by first manually marking an approximate position. Next, feature points are used to track the video relative to the background panorama. Since the video is captured at a different time and with different exposure timing, there may also be photometric differences. Photometric alignment helps remove this artifact. Masking out the background portions of the video improves this further by removing the motion-blurred background created by the moving camera. In our interactive application, a user can pan and zoom as usual to explore a gigapixel panorama. Embedded videos are initially shown with their first frame visible. Triggers make the video begin to play. In the case of videos that are recorded from a still camera, such as this park scene, they begin to play as one zooms into the location. In the case of this aeroplane where the camera is panning, the video playback is triggered by the view getting closer to the plane's path. A more common way to find video points of interest is to click on thumbnails of the videos. Let's look at this again to see what is happening. In this diagram, the brown rectangle represents the current view and the blue rectangles represent the video to be showed at time 0 and at time 1 when we wish the view to match the video. A simple linear interpolation creates a straight path. If we also move the view linearly in path length and the zoom linearly in time, we get this sequence of panned and zoomed views. Unfortunately, this path does not align with the video's path. Instead, we create a cubic Bezier curved path defined by a first control point in the current view, a final control point at the destination, a second control point that is free to move, and a third control point that can move along the tangent of the video's path. This creates a curved path, still using the linear speed and zoom graphs. If we now use a cubic curve to match the fact that the view starts out still and ends moving with the video, we obtain this path length function. For zooming, Igarashi showed how to maintain constant visual motion. We try to use this while still matching the zooming end conditions. This produces this modified sequence of views. We have captured 3 locations. In this scene, the user is exploring embedded video clips. Adding localized time-based elements brings gigapixel imagery to life. By carefully crafting the exploration of the space, we provide a balance between interactive control and reducing artifacts due to temporal boundaries.